Welcome to lesson 10, where we will be representing large numbers on the number line. We'll do this by visualizing large numbers on the number line using powers of 10. To be successful at this lesson, you'll be able to write a large number as a multiple of a power of 10. You can plot a multiple of a power of 10 on such a number line, and you can subdivide and label a number line between 0 and a power of 10 with a positive exponent into 10 equal intervals. We'll start by labeling tick marks on a given number line. That given number line looks like this. Pause the video, try and label the tick marks, and then we'll come back together to discuss. Okay, before we actually go through labeling this, let's just break down just a number line in general that is broken into 10 parts. It looks like something like this. Well, what if instead of saying it's going to be all the way up to 10, we change that to say 20? Well, we know that if we're going to break the number 20 into 10 parts, each part would have to be increments of 2, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So notice here that instead of writing it as 20, we have it written as 2 times 10, which is equivalent to 20, right? So 20 divided by 10, and we're increasing each of those increments by 2. Okay, so 2 times 1, 2 times 2, 2 times 3, etc. So let's kind of relate this to this number line here. We're now breaking 10 to the 7 into 10 parts. So 10 to the 7 divided by 10 is actually 10 to the 6. So again, relate that back to the one in blue, just kind of for a reference. So 10 to the 7 can also be written as 10 times 10 to the 6. Those two are equivalent, just like 20 is equivalent to 2 times 10. So with that being said, we can think of the tick mark before that as being 9 times 10 to the 6, 8 times 10 to the 6, 7 times 10 to the 6, and a continuous pattern. Right? So just kind of keep that in mind as we move through this lesson, because the big focus here is working with the number line. Okay, we're going to compare large numbers with the number line. You have the option of using the digital applet to help place the points on the number line. So they give you 5 different points here, and your goal is to place them accordingly to the number line, which looks very similar to what we just discussed in the warm-up. Take a moment to pause here and try it. If you can get through that first piece, then also try answering question 2 as well, and then we'll discuss both of those components when you're done. Okay, so again, from the warm-up, 10 to the 7 can also be written as 10 times 10 to the 6. So in the warm-up, we saw what that number line looked like, and we know that if that value is being multiplied by 10 to the 6, we can easily place that on the number line if it is between that 0 and 10, because it's broken into 10 parts. So we can write part A, which is 4 million, we can rewrite that to 4 times 10 to the 6. That would allow us to place this here on the number line. Part B is already being multiplied times 10 to the 6, so we can actually just go ahead and place that on the number line as well. Part C, 5 times 10 to the 5th. So we're multiplying 5 times 10, 5 times, right? So if we essentially were to rewrite this, we would have to move that decimal place once over to the left, which would give us 5 tenths times 10 to the 6. And so that would actually go between the 0 and that first part, 0 and 1 times 10 to the 6, essentially. It would fall right there. Here we would rewrite this to 7.5 times 10 to the 6. That would fall right here on the number line. And this last one, we would rewrite to 6 times 10 to the 6, and that would fall here on the number line. So it's always possible to rewrite an expression that is a multiple of a power of 10 so that the leading factor is between 1 and 10. And so by rewriting them, we are able to place them accordingly on the number line because of how it's broken into 10 parts, and each part is being multiplied by 10 to the 6 in order for us to place them accordingly. So let's kind of compare two numbers here, 4 million and 75 times 10 to the 5th, and let's estimate how many times larger one is than the other. So 75 times 10 to the 5th, or 4, 7.5 times 10 to the 6. It is about twice as large as 4 million because we can write that as 4 times 10 to the 6. 7.5 is close to 8, right? And 8 is roughly, 7.5 is roughly twice as large as 4. But because they're both being multiplied by 10 to the 6, it makes it easier to compare than in the form that they were originally in. So again, it's always possible to rewrite an expression that is a multiple of a power of 10 so that the leading factor is between 10 and 1. So 75 can be written as 7.5 times 10, those mean the same thing. And 6 tenths can be written as 6 times 10 to the negative first. So just keep that in mind as we move forward. Okay, so again, there's your criteria. We're working a lot with number lines today, and subdividing is going to be kind of the big focus of the next one. So we're looking at the speed of light here. As light moves through different materials, it slows down. The speed of light through empty space with nothing in its way is roughly 300 million meters per second. We can write 300 million as 3 times 10 to the 8th. The speed of light through olive oil is much slower. It's roughly 200 million, which we can say is 2 times 10 to the 8th meters per second. So let's first decide what power of 10 to use for the label of the rightmost tick mark on the number line so that the speed of light through space and through olive oil can be plotted. So since we obviously see we're working with values that are being multiplied by 10 to the 8th, we know that that's what's going to be the main component of our number line. So breaking it into 10 parts, this last component should be 10 to the 9th because 10 times 10 to the 8th is equivalent to 10 to the 9th, and we're breaking 10 to the 9th into 10 parts. Okay, you're going to pause the video here. You're going to work through the components of activity 10.3, and then we'll come back and kind of discuss and plot them on a number line. Okay, so we first are asked which is faster, light through diamond or light through ice, and how we can tell. So, okay, ice is already written as 2.3 times 10 to the 8th. Diamond is not, but again, it's easier to compare if they are both being multiplied by the same power of 10. So we can rewrite diamond to be 1.24 times 10 to the 8th. That would be equivalent. And through that, we can then say light travels faster through diamond. On the number line, we then see that it is subdivided because we're really looking at the values between 2 times 10 to the 8th and 3 times 10 to the 8th. So we would label those tick marks as such. Now we're looking at 2.1 times 10 to the 8th, 2.2 times 10 to the 8th, and so forth. Okay, so we're subdividing. We're really we're kind of like zooming in on the values between 2 times 10 to the 8th and 3 times 10 to the 8th. So let's go back here. We found the values for diamond and ice. We're going to go ahead and plot them here on the number line. So we can say ice falls here, and then diamond actually doesn't fall on that subdivided piece, which is actually question number 4. It says there's one speed that you cannot plot on the bottom number line. That's the diamond because it doesn't fall in that subdivided part. Okay, so now we need to go back here and kind of rewrite the rest of these materials so that way we can place them appropriately on the number line. So let's start with space. Space can be written as 3 times 10 to the 8th. Water can be written, water is already written as times 10 to the 8th, so we'll leave that there. Copper can be written as 2.8 times 10 to the 8th. And then olive oil can be written as 2 times 10 to the 8th. Okay, so again, just thinking about how many factors of 10 do I have to multiply 3 by in order to get it equal to 300 million. That's 8. Okay, so here's what this will look like when they're all plotted. So we can kind of now see in terms of light traveling through them. Diamond, light does travel through diamond the fastest. If we are comparing ice and diamond, light travels faster through diamond. And you can see that because when we're talking about speed, right, this means it's going through it faster because the value is smaller. Copper, it takes longest to travel through. So the purpose of this was to understand a few things. We wanted to understand how to express a large number as a multiple of a power of 10. We wanted to be able to find the given multiple of a power of 10. compare different, understand how to compare different large numbers by expressing them as multiples of the same power of 10. So a multiple of a power of 10 does not necessarily mean it's an integer multiple. So you saw when we plotted it, we had, 2.2, 2.3, 2.4, whatever those values were. It doesn't necessarily mean it's an integer. You will be asked to express numbers as multiples of a power of 10, which might mean writing something like 52,000 as 5.2 times 10 to the 4th. Using powers of 10, let's look at this value here. We can think of it as 23 million times 10. We can think of it as 2,300,000 times 10 squared. We can think of it as 2.3 times 10 to the 8th. And again, remember some of the components talked about writing that multiple of it between 1 and 10. If we use powers of 10 here, 5.4 times 10 to the 5th can be written in a couple of different ways as you see listed. Go ahead and read through that lesson summary if you choose to. Otherwise, you are successful if you are able to check off all 3 of these components from your criteria for today.